This is the second video for our Chapter 15 AP exam study. Here we'll take a look at the first free response question. So we have solid carbon and carbon dioxide gas at a high temperature placed in a rigid 2-liter container. Notice here's the solid, here's the CO2, which is a gas. And the reaction represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. And that's done in this graph here, or table here. When equilibrium was reached, there was still some carbon remaining in the container. Results are recorded. Notice at the beginning we have 5 atmospheres of pressure, and this atmospheres of pressure is due solely to the CO2. We have no CO at the beginning. Now as the reaction proceeds, we increase in the total pressure, which means we're losing some from the reactant, gaining some from the products. Because we have twice as many products as reactants, that's why our pressure is slowly going up. Notice the numbers have become constant at 8 and 10 hours, which means we have reached equilibrium. Equilibrium has been reached. Remember, at equilibrium, we just have both reactants and products now present. So, we want to first write the equilibrium expression. Let me pull this up a bit. Now, the expression, and this is commonly done in AP exams, is just the generic version of the equilibrium constant. No numbers yet. So, Kp in this case, because we have it in terms of pressures, we'll be putting a pressure up there and a pressure, so the pressure of the products divided by the pressure of the reactants. Our product is actually CO, and we have to square that because of the 2, and our reactant is CO2. So this would be the expression itself. If you were to do it in Kc, by the way, or they won't equal, but Kc would be expressed as the concentrations. Remember, you would put brackets for the CO squared and brackets for the CO2 if you were doing concentrations. There's 2 versions of the equilibrium constant, recall. So we want to calculate the number of moles of CO2 initially placed in the container. Now because we're told that we have 5 ATM, 5.0 ATM at the beginning, we know how much CO we have at the beginning. And since all these are gases, we're checking pressure, why don't we use PV and RT to do this? So actually you would require the use of PV and RT to find out moles, because they tell you the pressure, which is 5. They tell you the volume of the container in the problem, if you take a look, and they tell you the temperature. So we can solve for moles using PV and RT. So moles is PV over RT. R is a constant. You will be given this constant in the AP equations. So we have 5 for the pressure. This is atmospheres. We have 2.00 for the liters. We have 0.08. 21 for the R constant, and I'm doing this quickly for the sake of time, but go ahead and look these up. Our temperature is given as 1160. If you calculate this, you actually get yourself 0.105 moles of CO2 with 3 sig figs. Okay, so now for part C, we're asking for it says for the equilibrium mixture at the same temperature, the partial pressure of CO2 is then 1.63. So we're going to have to do a quick little icebox. Let's reproduce the equation so we can see it here. So our equation again is we have solid carbon in equilibrium, plus CO2, plus gaseous CO2, in equilibrium with gaseous CO. So if we set up the icebox, we're told that initially we have some solid carbon, so this is solid, so we won't care about the solid. It won't go into the equilibrium constant. But the CO2 is given to us as 5.00 and nothing of the CO. So as we reach equilibrium, notice it says we have 1.63 atmospheres of CO2. So this number right here is actually 1.63. So because we have that, we can figure the rest of it out, since we know we must have lost, if you take the difference between these two, 3.37. We must have gained twice as much, so double this and you get yourself 6.74, which means 6.74 would be the equilibrium pressure of carbon monoxide. So CO would be 6.74 atmospheres. The value of the equilibrium constant, we circle this, then we can plug this squared over this because it's a 2, so easily done. And just like we proposed up here at the beginning, so Kp would be 6.74 squared over 1.63, which gives us a fine value of 27.9. Remember, equilibrium constants have no units, so do not worry about the units. That was quick. That was done quickly. So look through it. Make sure you understand how it's done. If you take a look at the next one, D, if a suitable solid catalyst were placed in the reaction vessel, would the final pressure of the gas be greater than, less than, or equal? Now, it says here, assume that the volume of the catalyst is negligible. Because, again, if the volume of the catalyst is big, it can change the volume of the vessel. Since we have gaseous products and reactants, the volume can affect the pressure, which can affect the reaction. Here, but it says about compared to without the catalyst. Okay, so remember the catalysts don't actually change the amounts. Catalysts simply change the rate. These are related to the rate, chapter 14. So we'll assume, not assume, but we'll say that the equilibrium is reached faster. So same is the answer. Essentially, it'll be equal. So equal. And we'll have to explain catalysts allow equilibrium to be reached faster. Equilibrium to be reached faster, and that's what catalysts do. They speed up the rate of the reaction, but do not alter the equilibrium concentrations. But don't change equilibrium concentrations. Good? And then we have the last question here, E. In another experiment involving the same reaction, another 2-liter container initially had some carbon plus CO2 and and CO2 each at a partial pressure of 2 atmospheres. So this is 2 and this is 2. Remember, you can get to equilibrium either from the reactants or from the product side. You don't have to begin with all reactants. You can begin with all products and then go to the reactants. You can begin with a little bit of each. So what they're asking us is to predict whether CO2 will increase, decrease, or remain the same for the system as it approaches equilibrium. This is a reaction quotient problem. Remember, we would set up Q to see where we are compared to equilibrium, and then determine if we're going to go to the left or to the right of the reaction to get there. So Q is defined as products of reactants exactly the same way. So back to our reaction. Let's make sure we see that our reaction again is carbon plus CO2 in equilibrium with CO. That's 2CO. Right. So because carbon is a solid, we don't really care about it. But we want to calculate essentially 2 squared, because the 2 divided by 2. So products of reactants are going to be, again, CO, which is 2.0 squared divided by 2. Again, squared, because products have a 2 for the coefficients. This is easily done without a calculator. We get 4 divided by 2, which gives us 2. So 2 is the reaction quotient. Reaction quotient. And so we want to now compare this against K. Now we know that K, we calculated K above as 27.9. Now since K is higher than Q, in order for this reaction at this stage for Q to get to K, it has to increase. Notice the number has to increase, which means the products must increase, the reactants must decrease. So if the products increase, we're going to shift to the right, reducing how much CO2 will form. So CO2, or the pressure of CO2, will decrease. And then we want to justify that with this calculation. You can say because Q must increase to become K. And that's the idea. Remember, there was a shortcut to doing this. You could say that you can list K and Q in alphabetical order, and you see that K is greater than Q, so the reaction shifts to the right. Now, this won't be a good explanation. You want to definitely show your reaction quotient and compare it against the real K. All right, think through these. I worked these very quickly, but make sure you understand them all and come back for questions in class.